Okay. So we introduced the notion of a structure stiffness matrix. Okay. And we looked at DOFs and numbering. Okay, and the key is that you number free DOFs first, and then you number the restrained. DOFs next. Okay, so it gives a natural partitioning of the degrees of freedom, right? Displacements, the forces, and the partitioning of the stiffness matrix. Okay. Now I want to move to the next topic, and we're at page 218 of the notes, and we'll look at direct assembly. Okay, so basically I want to take you through the process that shows you how to construct the structure stiffness matrix. Okay. So the first thing I want to look at, right, is the picture that we drew during the previous lecture, right, which is right here. Okay, and I will focus on each one of the nodes, 1, 2, and 3. Okay, and what I'm going to do is I'm going to write the force equilibrium nodes. So force equilibrium. At nodes, right? And so if we look at node, let's start with 2, okay, because this is where degrees of freedom are free, right? Then P1, okay, must be such that it's offset by the sum of F3A and F3B. Okay. So the two X forces, right, reaction forces that that the internal structure, right, the structural element, exerts on that node must be balanced by the force that's applied at that node. Likewise, P2 must equal to F4A plus F4B. Okay. And then if you go to nodes 1 and 3, right, you find that each one only sees contribution from one element. So P3 must be balanced with F1A, P4 must be balanced with F2A, P5 must be balanced with F1B, and P6 must be balanced with F2B, like this. Okay. All right. So this equilibrium can actually be written in the matrix form. Okay. So you're starting to see the pattern, right, in this course, where P, okay, that's decomposed into PF and PD. Right. P1, P2, P3, P4, P5, and P6, like this. Okay. This is we draw the line between the free and restrained degrees of freedom, right? Equals 2. Okay. You can write a pretty large matrix. Okay. 6 by 4. Okay. And that matrix will go and will multiply the element forces. Okay. First, we're going to write down the ones coming from element A, right? And it's going to be F1, F2, F3, and F4. Okay. And next, we'll add the contribution coming from B. Okay, element B plus. Okay, same 6 by 4 guy times is F1, F2, F3, F4, right, coming from element B, like this, okay? Right, so just like we partitioned the 3 degrees of freedom, we'll partition this matrix too, okay? And then we just look at these equations, right? And we see that P1 on the element A, it only sees F3, which means that the first column, first two entries are 0. Then this is the one that will hit F3. Okay, it depends on nothing else, right? P2 depends on F4. It means that the first 3 entries are 0, and we have a 1 here. Okay. Then P3, P4, P5, P6, right? From the element A, only P3 and P4 will be affected, right? And the entries are 1 and 2, respectively. This translates into the following structure: 0, 1, 0, 0, right? And then the last 2 entries of the global force vector are not affected. It's like this. Okay. Likewise here. Okay. Again, P1 is affected by F3, P2 by F4. Right, so we pick up the same structure here, 0, 1, 0, 0, 0, 0, 1, okay? Then P3 and P4 are independent of element B, okay, which means that we pick up 2 rows of zeros, okay? And then finally, P5 and P6 depend on F1 and F2. Right, so we pick up 1 here, zeros, 0, 1, 0, like this, okay? Okay. And so what this does, right, it produces 2 matrices for us. The top part, I'm going to call matrix A, okay? Comes from element A, right? I'm going to call it transpose. Okay, you'll see why later. Then I have a subscript B for Boolean and F for free. Okay, the bottom submatrix I'm still going to call A. It's still Boolean, right? B, D for restrained degrees of freedom, still comes from element A and still transpose. Okay. Likewise here, this submatrix is going to be called A, coming now from element B, still Boolean, F for free, transpose, and this part is BD, coming from element B and transpose. Okay. Right, so then we can see, right, if we're interested in the contributions to PF from a given element E, right, these contributions can be expressed by another matrix vector multiply that looks like this: ABF, coming from that element, generic, transpose, times the vector of element forces, like this. Okay. And the same equation holds for D. A, B, D, transpose F sub E. Good. Okay. Now, for every one of the elements, right, if we look at the element force, F okay, let me recall from the previous lecture. I can get it by taking gamma ROT, transpose, gamma RBM, transpose, times the basic force. Okay. If you look at the structure of this matrix here, right, gamma ROT equals to delta X over L, right? Delta y over L minus delta y over L, delta x over L, 0, 0, 0, 0. Okay. Then I have a 2 by 2 0 block here, and delta x over L, delta y over L, minus delta y over L, delta x over L, 4 by 4. Right. RBM is minus 1, 0, 1, 0. Okay, like that. So if I take the matrix gamma transpose, okay, and I define it as gamma ROT transpose times gamma RBM, okay, you get something that looks like this. Just do a straight up multiplication, okay, and you obtain minus delta x over L minus delta y over L, delta x over L, and delta y over L. Okay, good. Okay. And so then, if we revisit the vector P, okay, which was PF, right, and PD, okay, right. This guy can be written as A B F, right, for element A transpose, A B D for element A transpose. Right. It goes and multiplies F sub A, right, but F sub A can be written as gamma transpose for element A, right, times basic force at element A. Okay. And then you add the contribution from the element B. ABFB transpose, ABDB transpose, right, times gamma transpose for element B times F prime underbar for element B. Okay, and so basically the applied forces, right, must be such that the basic element forces are balanced in the following fashion. Okay. So let me leave it at this for a second. Let's approach it from the other side. Okay. Compatibility. Okay. It's a very important concept. Right. And what it says is this. Right. If I have a structure like that, okay, in the undeformed configuration, okay, and then this node goes, right, and moves, let's say, to the right and up, okay, by an amount U1 and U2, right, so say it's somewhere here, right, this is going to be a new structure like this, okay, right. And then likewise, right, if you look at each individual element, okay, This guy moves here, this guy moves there, right? So it develops delta 3a, delta 4a, right? And then delta 3b, delta 4b. Okay? And so both this point and this point, right, displace to this location here. Right? So this becomes a new element A, this becomes a new element B. Okay? But the point is, this point occupied the same location in space prior to displacement, okay? And then it occupies the same location in space after displacement. Okay? It means that whatever delta 3a is, okay, it must equal to delta 3b, right? Meaning the displacement of the same point in the reference configuration has to be the same, right? Otherwise the structure falls apart and you want to avoid it, okay? And that guy has to match the global displacement of u1. Okay? This is what happens in x direction, and then the same thing happens in y direction. Delta 4a must equal to delta 4b must equal to u2. Okay? So this is compatibility between structure level and element level displacements. And the clue is it's in the global coordinate system. Okay? Right. Good. And so then you can go and express the displacement vector, right, in the global coordinate system for element A. We can write it out, delta 1, delta 2, delta 3, delta 4, right, for element A. Okay? And what you find, right, is another way to write these equations is to again re-express things in a matrix vector form. U1, U2. Right? The first two are restrained, so nothing happens here. Right? Then U3 must equal delta 3 must equal to U1, so you get a 1 here, and delta 4 must equal to U2. Okay, you get a 1 there. Okay. And what you find that this is exactly A, B, F for element A times UF. Okay. So, right, you use ABFs to express the force balance, right? And you also use the ABFs, these A matrices, the Boolean matrices, right, in their transposed fashion to express displacement compatibility. Okay? And so likewise, right, if you look at the entries of the delta B vector, delta 1, delta 2, delta 3, and delta 4, okay, for element B, okay, you get a matrix times U1 and U2, okay, and you get, again, by coincidence, the same structure, 1, 0, 0, 1, okay, and this is exactly a BF for element B, okay, Boolean matrix. Okay, good. Right, so then you need two more relationships. Okay. One is, okay, if you want to obtain the basic displacement for any element E, right, the way you do this is you start with a global for element E. Right? You multiply this by the rotation for element E, right? And then you multiply this by RBM, Okay, we covered this multiple times. Okay, this is the same as matrix gamma E. Okay. Right, and then finally, F over bar prime E equals kappa over bar prime for element E times delta prime for element E. Okay. And so then for our example, E equals A or B, right, in this case. And so now let's start putting things together. Okay. So we stopped, right, at this expression here, right? For every one of those, let's use K prime B delta prime over bar B, right? This becomes K prime A delta over bar prime A, okay? Right, so now at the basic level, I introduce my sort of, I guess, constitutive law, right? Remember, this comes from the differential equations, right? And then we can take these displacements, right, and kind of work our way up back to UF, okay, using the compatibility expressions, right, the ABFs, right, and then this guy here, okay. Right. And so what we find, right, is that PF, let's just focus on the free forces applied at free nodes, okay, equals to ABFA transpose gamma transpose for element A, right? Then you get kappa prime A gamma A times ABF A, right, acting on UF, right? Contribution from element A and contribution from element B looks like this: ABFB transpose gamma B transpose kappa over bar prime B gamma B ABFB UF. Okay. And so now you can see that on the left-hand side you have the forces, right? Here you have this product of 5 matrices that multiplies the free displacements, right? Free degrees of freedom, right? There's another product of 5 matrices that multiplies the same thing, okay? And so what I can do now, right, is erase this here, right? Put a big parenthesis around this object, okay, and put UF here, okay? And so what emerges, right, is exactly our structure stiffness matrix. Okay, so for our example, this is exactly, right, K, F, F, right? That relates the displacements at 3 degrees of freedom to the corresponding applied forces. Okay. What we also recognize here, right, is this is exactly stiffness matrix in global coordinates for element A, right? And this guy is exactly stiffness matrix in global coordinates for element B. Okay. And so KFF equals to ABF element A transpose, right? K for element A, BF, element A, plus A, BF, element B, transpose K for element B, A, BF for element B, like this. Okay. So what does that mean? Structure stiffness matrix, right, equals to the sum of individual element stiffness matrices, okay? But that sum is sort of modified by the presence of these Boolean matrices, okay? So what's happening here, right? These Boolean matrices take the element level stiffness matrix, right, which for a truss is always 4 by 4, okay? And by pre and post multiplying by ABF and ABF transpose, right, what this operation does, right, it takes the entries of the element stiffness matrix and places them in the appropriate locations of the structure stiffness matrix, okay? And so now this object has the right structure, right, and the right dimensions, can be added to the structure stiffness matrix. And then the same thing happens to element B, right? You build up its local element stiffness matrix, but in global coordinates, and then you use these Boolean matrices to go and sort of send things in the proper locations of the global stiffness matrix, right? And once you have that object, you can add them together. Okay, so first thing you learn is that the structure, basically this is the biggest takeaway, right? Stiffness matrix, right, equals to the sum of element stiffness matrices. Okay, but sum, right, I'm going to put it in quotes, right? It's sum provided the matrix is transformed to have the appropriate dimension using these Boolean operations, right? And it means that in general, okay, if you look at the structure sort of with an arbitrary number, right, of arbitrary DOFs, right, arbitrarily complex structure. So if NEL would be the number of structural elements that are employed, then KFF becomes sum E of 1 to NEL, right? So not just of 2, as was an example. In general, would be a sum over NEL. For each one of the elements, you're going to have a Boolean matrix, A, BF, okay, E transpose. Then you would take the matrix KE, and then you would post multiply it by ABFE, like this. Okay, and so this is a general result that I wanted to present. Okay, now let me close this lecture by saying that ABF E, right, sort of is good to show formal manipulations, okay, to arrive at this form, right, and to explain, right, that you can't, you need an object of one size on the left, right, KEs have a different size, right, and AEs kind of bring things to the right, locations and to the right size, right, but never used in practice. Okay, so there's another, right, which means that rather than using ABFs explicitly, you need something else, okay, and this something else would lead to some of the key data structures. Okay, that are used in structural analysis that I will present at the next lecture.